What I would like to do in this video is to explicitly verify Gauss's divergence theorem using an example of a somewhat simple vector field. The most general vector field can have x, y, and z components. In each of the x, y, and z components, it can be a function of x, y, and z. I will take the x component to be a function of just x and z, the y component to be a function of x and y, and the z component to be a function of x and z, just to keep the computations somewhat simple. And we're going to verify the divergence theorem. It's valid for any surface and any volume contained within that surface, but we're going to take as the simplest possible example a cube with one of the vertices at the origin and a cube of unit side. So really, how do you find the what's the divergence theorem? Let's recall that first. It's a statement that the oriented double integral over the surface of the cube, meaning the six faces of the cube of the vector field dotted with the area vectors dA, or we can write this in my notation which I have used in my notes and in the earlier videos as v dot n d sigma. In other words, I'm writing the area vector dA as some unit vector n hat times d sigma, where n hat is the direction in which the area vector is pointing, and d sigma is just some measure on the surface. In this case, since it's a cube, it's going to be a Cartesian measure like dx, dy, etc. So that is the left-hand side of Gauss's law. We'll call this the left-hand side. And the right-hand side of Gauss's law is the computation of the divergence of the vector field over the volume V. So maybe I should call this VOL because I've already called V the vector field. So VOL of the divergence of V d tau, tau being the volume element. So it's going to be some, in this case, it's going to be dx, dy, dz. All right, so how do you, obviously the right-hand side seems almost immediate. All you have to do is take the divergence of the vector field and then integrate over the volume. So the right-hand side is always going to be the easier calculation. That's the utility of Gauss's law, to find something as complicated as the left-hand side, which in most applications turns out to be something like the flux. All you would have to do is compute the right-hand side, which in many physical applications turns out to be the enclosed charge or something that's enclosed. So if this were an electric field, V were an electric field, then this would be the charge enclosed divided by epsilon naught, which is the constant of nature. Let's just try to figure out how to do a computation as simple as this. And in your homework, you'll have more complicated shapes. So the unit vectors, each of these area vectors can be written. So let me start by writing the top. Top is going to have the coordinates x and y because it's parallel to the xy plane. So it's going to be dx, dy in the k hat direction. The moment I write top, I can immediately write down. Because it's in the minus k hat direction. Now I have to do the right and the left, and then front and the back. So dA right, the right face is parallel to the xz plane. So it's going to be dx, dz in the direction of j hat, and then immediately do the other one, which is the left, is going to be dx, dz in the negative j hat direction. Lastly, I have front and back. So I'll do the front first, and the back will just be the opposite. So dA front, the front face is parallel to the yz plane. So it'll be dy, dz, k hat, I hat, and then dA back will be dy dz negative I hat. In this manner, we have found all the area vectors that we need for the left-hand side computation. So it just amounts to writing the left-hand side out now in full detail. So you're going to have 6 integrals. The integral over the top surface. Now, if I do the top surface, I'm going to pick up only the k hat components. So the I hat and the j hat components will not interact because I hat dot k hat is 0, I hat dot j hat is 0, k hat dot j hat is 0. So the only thing that's going to be 1 is k hat dot k hat. So I'm only going to pick up the vz component. So I'll get vz and then I'll have dx dy plus, let's do the integral on the down. Same thing. I'll get vz, but let's evaluate this vz. This on the top surface is defined by the equation z equals 1. Z equals 1 is a plane that's parallel to the xy plane. So z equals 1 is what we need here. And the down is defined by z equals 0 of the same with the negative sign because of the negative k hat. So dx dy. We'll proceed like this to write the others. Let's go exactly like this. So I'll go first with right. Right will only pick up the j hat component, so it won't pick up either this or that. So I'll write that next. On the right face, I'll have vy evaluated at the right face is defined by y equals 1. Dx dz, and then the left face, which would be vy at y equals 0, negative dx dz, because of the negative sign there. Last item is front and back. Front and back are I hats, so they're only going to pick up vx. Vx evaluated for the front surface, the definition is x equals 1, picks up the front surface, and I get dy dz plus the double integral over the back surface, which is defined by being at x equals 0, negative dy dz. So these are the 6 integrals we have to solve. Let's do that. First of all, vz is x squared z. So vz at z equals 1 means you just get negative x squared. So that's going to be the integral over the top surface, negative x squared dx dy. Now what about this one at z equals 0? At z equals 0, vz is simply 0. So this doesn't contribute at all. Third integral, vy at y equals 1 is just x squared. So that's going to be the double integral over the x squared dx dz. And vy at y equals 0 is simply 0. So that also is a big fat 0. Now this one, vx at x equals 1, so you can see it's drastically simplifying already, is going to be 2 minus z, because when I put x equals 1, I'll get 2 times 1 minus z. So that's 2 minus z dy dz. And at x equals 0, that part just disappears and I'll just get minus z, which, by the way, minus z combines with the minus sign over there to give me plus. So I'll write it as plus z dy dz over the back surface. Now it's just a matter of evaluating these integrals. These integrals are not terribly hard to evaluate, so I'll just do them all in one line, I guess. The first integral The top surface, remember, the x coordinate is going from always from 0 to 1, and the y coordinates also always going from 0 to 1, and the z coordinates also going from 0 to 1. So all these integrals are from 0 to 1. I can do the y coordinate first from 0 to 1 because that's just dy, and that'll give me 1. If I do the x coordinate from 0 to 1, I'm going to get, let me write something, 0 to 1 dy integral 0 to 1 x squared dx. So they sort of decouple. We are lucky here because it's rectangular coordinates, so things nicely decouple here. And for the right surface, you again have the same type of deal. I'm going to get integral 0 to 1 of dz integral 0 to 1 of x squared dx. So you can immediately see these two just cancel out. Plus 0, I won't write that plus 0. And then I'm going to get this one, this integral here. So let me just create some boundaries. Plus I'll write plus 0 for this one. And then this here is the integral of dz will interact with this, but dy will not. So I'll write it as 0 to 1 dy integral 0 to 1 2 minus z dz. Possibly the only non-trivial integral there. And then here I have dy decouples nicely, and I have integral 0 to 1 z dz. Okay, so those are the only two integrals that's going to give us some non-zero values. Let's see what it is. Dy integral 0 to 1 is just 1. 2 minus z, when integrated, I'll get 2z minus z squared over 2 from 0 to 1. And here, I get just y from 0 to 1, which is just 1, times this quantity here, which is z squared over 2 from 0 to 1. So basically, these two cancel out, and I get 2 from 0 to 1, which is just 2. That's the answer for the left-hand side. For the right-hand side, we have to calculate the divergence of the vector field. So let me write what that is. The divergence of the vector field, by definition, the divergence is just the partial derivative of the x component plus the partial derivative of the y component plus the partial derivative with respect to z of the z component. That's all it is. So let's find out what that is. Del x is del x of vx is that. Del y of vy is that, and del z of vz is that. So this is just a bunch of differentiation. The x derivative of 2x minus z is just, it doesn't act on the z, so it produces a 0 there. Z should be thought of as a constant. This just gives me 2. That's really what we want. So hopefully these two will cancel out. So del y gives me x squared, and del z gives me minus x squared. And sure enough, they do cancel out, and I get 2. Now all we have to do is the right-hand side, the proper, is the triple integral over the volume of del dot v d tau. But del dot v is 2. So it can be taken outside, and I get 2 times the triple integral over the volume of a cube. Well, everybody knows the volume of a cube. It's just 1 times 1 times 1. In this manner, we have shown that the left-hand side of Gauss's law equals the right-hand side of Gauss's law. And we have explicitly verified the Gauss's divergence theorem. Not that it requires such verification. It is always true. It's a mathematical theorem. But it's nice to see. The scale of effort involved on the left-hand side is tremendous. And when you do the homework problems where you have things like ellipsoids, just finding these normal vectors is a headache. You've got to use the concept of gradient to find even the normal vectors, the n hats. And then doing all the integrals on the left side, it's not trivial. And sometimes you may have to use Wolfram alpha for that. The right side almost always falls out just like a low-hanging fruit. And so that's the big advantage of Gauss's divergence theorem. One of the sides is almost always much easier to compute than the other side. By the way, it's always not the right-hand side that's easy to compute. In some examples, especially in physics, it's actually the left-hand side that's quite easy to compute.